Hey there, welcome to a video discussing pages 5, 6, and 7 of the section 7.4 notes. So here we're looking at example 5. You're asked to solve for y of dy over dx equals e raised to 2x minus y power, and with the initial condition that y equals 3 when x equals 0, and also state the domain over which the solution is valid. So we haven't really done these differential equations with exponential expressions, so we'll do that right now. So as usual, we want to separate x and y. A little hard to do that as is. So what we could do is rewrite this as e to the 2x over e to the y. So remember your properties of exponents, right? You have a to the m over b to the n. Sorry, I meant to make those bases the same. Over a to the n, you're allowed to subtract those exponents. So if you have a power in which the exponents are expressed as a difference, in this case 2x minus y, you can break it up as a ratio with the same base, e to the 2x or e to the y. Now we separate. Remember, that was our first step, to separate. So we're going to write that in red. Remember, then you want to integrate, then sub, and then isolate. Those are our 4 steps. So now I want to integrate. I'm doing the integral of each side. Now I want to integrate the left side, just e to the y. That's just it. When I integrate the other side, it's going to be e to the 2x over 2, because it is like a u sub in a way. If you let u equal 2x, then d over dx equals 2. So du is 2 dx, or dx is d over 2. But instead of going through all that trouble, whenever you have a linear term, like as an exponent or something like that, you could just do the antiderivative like you usually would, but then of course just divide by the coefficient of x. Because if you take derivative e to the 2x over 2, you get e to the 2x. And of course plus c. Now let's substitute our initial condition. You have e cubed equals e to the 0 power to 2 plus c. So c is going to equal e cubed minus 1/2. And my apologies, I think that's my daughter crying in the background, so don't mind that. So c equals e cubed minus 1/2. Now we have to isolate y. So our equation again is going to be e to the y. Let's actually change colors again. So e to the y equals e to the 2x over 2. Your c value is this, e cubed minus 1/2. So what you could do is you could write as y equals the natural log. So essentially what you're doing is you could take the natural log of both sides to move the y to the front. You have the liberty of doing that. Or you could think of it as, well, e to the y equals all this junk. So y is going to be log base e of all that junk, because all that junk equals e to the y. So you could, rewrite it as a log equation as well. So y will equal natural log of all that junk. Now in this case, there's no reason why there should be any restriction for x, because x is an exponent, so we could really, and you don't have the x in the denominator at all. So really your domain is going to be all real numbers. So we're totally fine with that. Or you could write it like this, negative infinity to infinity, if you so desire. But that is your answer, natural log of all that junk. You don't need an absolute value around it. I mean, yeah, you need to guarantee that x stays positive, but that's kind of somewhat implied. I mean, we wouldn't plug in anything negative for x anyway. So Oh, actually, it wouldn't have mattered because e to whatever, actually, let me take it back. E to whatever is still positive, right? Because e is a positive number itself. So yeah, everything stays positive here. And plus e3 minus 1/2, that's a positive constant. So yeah, so you don't have to worry about logging in negative numbers, so we don't have any restrictions in our domain. Actually, I'll ask that in the Google form. Okay, let's keep moving. This one's a little more general, and it kind of leads us to what we're going to talk about on the next page. So for example 6, you're asked to solve for y dy over dt equals ky. This is an initial condition right here as well. So what we're going to do is we're going to separate. We're going to move the y to the left side, keep the k on the right side, move dt over. I'm going to integrate both sides. But before I do that, it just helps to maybe rewrite like this. So right side k times t plus c, because you have a constant. This is natural log of absolute of y on the left side. So absolute of y is going to equal e to all that junk, e to the kt plus c power. And you are at liberty to actually break that apart as e to the kt times e to the c. And e to the c, we can consider to be a constant because e is, the constant itself. Now you have your initial condition, so now we substitute. When I substitute, I'm going to replace y with y0 and 0 and t with 0. So absolute value of y sub 0 is going to equal e to the k times, which is 1, times e to the c. And if you were to actually isolate c, you would take the log of both sides. So c would be the natural log of absolute value of y sub 0. The reason why that is true, because remember, e to the c equals this. So you take natural log of both sides. The c rolls to the front. You have c times natural log of which is 1, and you have natural log of absolute value of y sub 0. So now, when I try solving this, absolute value of y equals e to the kt times e. And remember, c equals natural log of y sub 0. But when you have e and ln, you have ln in the exponent for e, those actually kind of cross each other out. So it becomes y sub 0 times e kt. And that's the absolute of y. T could be whatever. So your domain for t is going to be all real numbers. So t could be whatever you want. So that would be the solution to that differential equation. So it leads us to the next page. And this is something called the law of exponential change. Now, what this tells us, when dy over dt equals k times y, k is a constant. So it tells us that dy over dt is proportional to y. That's because dy over dt divided by y equals the constant, which is k. So if a is proportional to b, then you can say a over b is equal to k. So it's the same kind of reasoning there. So in other words, the rate of change of y is proportional to y itself, because the rate of change of y is dy over dt, and of course that's y itself. So this situation occurs in many real-life applications, and the solution we found in example 6 is called the law of exponential change, which we just solved. So when you have dy over dt equals a constant times y, you're allowed to actually write this as your solution. So here you can see I got rid of the absolute value. I guess the assumption is that you're dealing with a positive value for y, so you kind of worry about it. And remember, if your k is positive, that means that you have a positive change, so it's growth. If your k is negative, I shouldn't say remember, because you probably haven't seen it in this way before. But you have talked about growth and decay exponential bunches in the past. But if your k is positive, your rate of change is positive here. So that's considered growth. If it's negative, then it's considered decay. I'll ask that also as a Google form question. And again, the initial condition is that y equals y0 when t equals 0, because if t equals 0, you have e raised to the 0 power. So now you can just kind of assume this solution. You don't even have to go through the whole motion of separating, integrating, substituting, isolating. You can just kind of just go straight to it. So let's do this for example 7 now. So for example 7, find the solution to this differential equation with these conditions here. Well, I already know now that the answer is y equals y sub 0 times e kt. But let's put in these initial conditions here. So 70 equals y sub 0 equals e k times 1. So y sub 0 equals ek. That's 70. Also, let's plug in this condition. 280 equals y sub 0 times e to the 10k power. Well, what you could do is you get a little creative here. If you stack these two equations together and actually divide them out, you get 280 over 70 equals y sub 0 times e 10k. You can substitute also if you want. It's up to you how you want to do it. But you can get even more creative like how I'm doing it here. So you get 4, y sub 0's cancel, and you subtract those exponents, e to the 9k. So 9k equals natural log of 4. K is natural log of 4 divided by 9. So your constant is going to be kind of a wacky decimal. If I do natural log of 4 divided by 9, I do get 0.154. So that's my constant here. And so the solution to my equation will be y equals y sub 0, which I still need to figure out, times e to 0.154 t. Now solve for y sub 0. I can use either, let me use red here. I can use either this one or the one right below it to solve for y sub 0. If I use one right below it, 70 equals y sub 0 times e to the 0.154. So if I do e to that power, and this 70 divided by that number, actually I get 60.007. That's y sub 0. So that's my answer. Y equals 60.007 times e to the 0.154 t. And if you want, you could plug in 1 for t and see if you get 70. Plug in 10 for t and see if you get 280. And you should. And very important that when I solve for this here, I didn't round too soon. I actually kind of kept it in my calculator as 0.154032768. And then I divide that, did 70 divided by that number by doing 70 divided by my previous answer. That way, or sorry, did e to that number, e to the 0.154032768. But I kind of kept this intact when I rose e to that power. So I didn't round too soon. And I'll ask that as a Google form. So if you do round too soon, your answer might be a little off at the end here when you're solving for the initial value. So be mindful about that. Because the College Board would actually take off a point if you don't have this round to 3 decimal places correctly. So you don't want to round too soon. That would not be good. Okay, we're at the home stretch here. So we'll do 3 quick examples that just use the same kind of general solution. So here, again, our solution is going to be y equals y sub 0 times ekt. Now you're told half-life. Half-life is a very popular application. Some element or isotope is 1.92 years, find k. So what this means is that y is half of the additional amount when t equals 1.92. So that's what I'm going to do. I'm going to replace y with 1/2 y sub 0 equals y sub 0 times e 1.92k. The y sub 0's will cancel. Half equals 1.92k, e to 1.92k. Take natural log of both sides and divide by 1.92. If you do that carefully, natural log of 0.5, which I think is 0.693, Yeah, it's a very popular solution, negative 0.693 actually, divided by 1.92. So your k should be negative because it is decay. You are losing this amount as time passes, so it's negative 0.361. Here's another application. So Sapphire worm computer virus hit the internet many years ago. Studies suggested the first few minutes of number of n capital N is the number of infected computer hosts, be modeled by the following differential equation, where t is measured in seconds. So this happened pretty fast. So when do we have a double time? Well, notice you have dn over dt instead of dy over dt, but you still have the same kind of form. It's k times your variable. So it's still the same solution that we're seeing already. So you're going to do is you're going to say n for part A, n equals n sub 0 times ekt. Now, if you're doubling, that means n's going to be double the initial amount. Remember, n0 is the initial amount. So 2 times n sub 0 equals n sub 0 times e. And this is k. So k is 0.0815, and you're solving for time. N0's cancel. Natural log of 2 equals 0.0815 t. So you take natural log of 2, divide by 0.80815, and you get, let's try that again, natural log of 2, divide by 0.0815, and you get 8.505 years. Sorry, seconds, my bad. So it didn't take very long for double the computers to be infected with the virus. Then for part B, if you began with 4 computers, how many were infected after 3 minutes? Well, 3 minutes is 180 seconds. Remember, we're doing this in terms of seconds, right? Because that's how the problem is defined. So for part B, n equals 4 computers times e. Our k value, remember, is 0.0815 times 180. You're going to see a lot of computers are infected. So it's very rapid. So if I do e 0.0815 times 180 times 4, yikes, you see 9.4 million computers were infected. 9,400,697, roughly, we're rounding up, computers were infected. That's crazy. So that's the beauty about integration, is that we use integration to get us a solution to this differential equation. And this differential equation represents, remember, a rate of change equaling a constant times the variable in question, the number of computers infected or something like that. So if you find that things are changing in that manner, now you have the general solution, which you can just go straight to right away. We actually worked on example 6, but now you can actually, I meant to say example 7. No, that was example 6. And you can go straight to it and then just apply it. Last bit, we're seeing the same thing. You're told what general solution is. We know what it is. So write solutions to the following. So you could just say this: P equals P sub 0 times e to negative 0.2 t. Here you can say L equals L sub 0 times e, and you're using a w as a variable here, 0.61 times w. Here you can say y equals y sub 0 times e. Now you have a negative here, so do negative k t. And then finally for d, you say n equals n sub 0 times e. You have k value is 0.8 t. So that's how you can actually do all these very quickly. And the plus c you don't have to worry about because it's kind of already covered in the concept itself. And actually, the multiplying factor right there. So anyway, so that's it. That concludes the video.